Hey everybody, the purpose of this video is to walk you through a solution to question 415.2 in the Collaborative Statistics textbook. This one involves expected value of a die game. It's going to be kind of like the one we did in class, but a little bit more simple just because it's only got one die versus three. So you're going to roll a die and your payouts vary depending on what you get. So just like we did in class, I'm going to create a little bit of an extraneous column over here to keep track of the rolls. So what we're going to have is we're going to have a number rolled over here. And when you roll a die, assuming it's fair, 1, 2, 3, 4, 5, and 6. And what I'm going to do is I'm going to start the distribution going over here. And we'll keep track of stuff over here. We're going to kind of answer this. There's a bunch of different parts. There's 6 parts to the question. We're going to kind of answer them all at once. The first thing it asks is, what are you ultimately interested in here? The value of the roll or the money that you win? Well, I think it's pretty clear. The roll isn't important. It's how much you get or give as a result. So what we're really interested in is going to be the average winnings, which is all you can really talk about. I mean, if you try to talk about an individual event, the individual of taking one die and rolling it one time, I mean, there's 3 things that can happen. You're either going to win 10 bucks, win 5, or pay 6. I mean, but chances are you're not going to play the game one time. First of all, you're interested in, is the game overall a good idea? So what we're shooting for here is your average winnings. And you know, winnings might be negative. I mean, that's the whole point. It might be a negative winning overall. So anyway, let's put it together here. Part B, define the random variable x. Well, this is kind of why I decided to put an extra column over here, number rolled. We don't care about that. We care about how much money, which is kind of what part A was about. So what we're interested in is the amount that we win on any particular roll. There's your random variable. Call it a random variable because you know it's going to be 1 through 6. That much is determined. What you don't know is which one it's going to be. List the values x may take on. Okay, so according to the rules, if I roll a 6, I win 10 bucks. If I roll a 4 or a 5, I win 5. And if I do anything else, I pay 6. Interesting game. Said a different way, maybe you paid 6 bucks to play the game, but you won 11 if you roll 4 or 5, or 16 if you roll a 6. That would clear these winnings, excuse me, pay 6. Those should be negative. Big difference, big difference. So I'm guessing that the negative 6 loss could be the ante. So your ante is $6 if you cleared 11. Anyway, regardless, these are going to be your random variable values. The probabilities for each of these are going to be 1/6. Now, you could also, should you choose, you could make this actually a probability table that only consists of three events. We'll talk about that in a second. We do the mathematics. It says construct a PDF. Side note, what your book calls a PDF, we just did. Now, a PDF technically is called a probability density function, and that would be a function, an actual equation. I'm not going to ask you to do that. But just realize that when you talk about what are called PDFs, that those are actually equations that are generated. It says, this is the key question, E. Over the long run of playing this game, what are your expected average winnings per game? And that's where this comes in. We have to use this PDF. Average winnings per game. Okay, so what we're going to do is, we're going to use that idea of a weighted average, because that's all this is. It's a weighted average. So I'm going to make it a little bit more concise by doing the sum of this times this, plus this times this, plus this times this. But I can group that together using distributive property. That's going to be negative $6 times a half. Make sure you buy that. Make sure you buy the negative $6 times a half. It's 3/6. So this one plus this one plus this one is actually 1/2, 3/6. So half the time you're going to lose 6 bucks. Plus, looks like a third of the time you're going to win 5. Plus 1/6 of the time, you're going to win 10. Let me back away here for a second. back way so you can see that. That's going to be the mathematical construction of the average. Be the same exact thing you got if you did this times this plus this times this plus this times this all the way down. With me so far? Okay, cool. So now all we got to do is simplify all this down and get ourselves a decimal representation of what's going on. So this is going to be negative $3. So I can fit all this on the board. Negative 3. I'm not going to put an equal sign here. I'm going to write this in a different color next to it so it jumps out. So this is negative $3. 5 times a third gives me, what is that? 5/3 is about $1.67. It's about $1.67. Pretend that 7's on the board. And then 10 times 6, that's $1 plus what? 4/6 of $1. 4/6 $1.67 as well. So that's also $1.67. Yep. Duh. That's half as big and that's twice as much. It's $1.67. Okay. So I want you to understand what these three pieces mean. The negative $3 represents the amount of money on average that is lost by rolling 1, 2, or 3. So over time, those three numbers on the die, I guess, are contributing to a loss of $3 on average. Okay, with me so far? Good. Over time, the 4 and 5 are creating a gain of $1.67 on average. $1.67 on average. And over time, the 6 is generating a gain of $1.67 on average. Cool so far? All right, good. So now, by summing all this up, we've got 3, actually we can do this pretty nicely. It's just 10/3 minus the 3. So we know this is going to be positive, isn't it? 10/3 is about that's going to cancel the 3. The 10/3, the 9/3 is going to cancel the negative 3 that's up here, and we're going to be left with about a positive 33 cents. That's your expected winnings per game. Well, heck, that's actually a good thing because it's positive. That means, yeah, you're going to lose half the time. You're going to lose money half the time. But the actual amount that's paid for you here in the winnings column is large enough to offset that. So your winnings here and here, the $1.67 added together, are more than $3. So that more than $3 actually offsets the $3 loss up top. Well, heck yeah, part F. Should you take the deal? Now, you got to realize, half the time you're going to lose, half the time you're going to win. Okay? Half the time you're going to lose, you're losing $6. Of the half the time you win less than $6. It's kind of hard to process that all at once. So should you take the deal? I would take this deal. This is Sean speaking. I would take this deal because how many investments do you guys have that guarantee you a rate of return of like this? Especially because there's no ante on this game, right? Assuming there's no ante on this game. Now, even if there were an ante, the expected value is positive. It means if you play this game enough, you're going to walk away with $0.33 every time you play. So heck, just keep playing, if you can. This is one of those kinds of things like the in-class quiz we did where the kids in New York paid attention and they realized they could make a lot of money if they just paid attention to the payouts. These payouts are such that you're averaging $0.33, about 33 cents per game. I say, yeah, part F, let's take this deal. Let's take this deal because on average we're going to make money. All right? Hope that helped. You can also, if you don't want to do all the mathematics for this one, you can also go L1 and L2 to get your distribution taken care of. Clearly run one bar stats and it'll pop that number out. I like, at least for one of these problems, looking at it this way though, because by seeing it this way, you see the component pieces of the distribution and you can actually kind of see how everything fleshes out. So, I hope it helped.